36. 6 to 36. Similar way will give us that CV not at PT. What would this CV as a function of?
Molar volume and temperature.
Molar volume and temperature. Exactly. If we have problems with pressure and temperature, we use Cp. If you have problems with molar volume and temperature, we use Cp. So, Cv star, Cv at molar volume and temperature equals Cv star at that temperature plus T integral, and here will be molar volume going to infinity, which is the ideal gas condition with respect to molar volume. Two limits that give us ideal gas. Pressure goes to 0, or molar volume goes to infinity. What does it mean, ideal gas? Physical. Means that molecules are not affected by other molecules. When does that happen? When you have extremely low density of molecules in a given space. So you can achieve that by either low pressure or huge volume. So V molar goes to infinity T to whatever is the molar volume that we have T, and now that's a partial of second partial of pressure with respect to temperature at constant V molar dV. And this is really a final form, this equation 6 to, don't have an equation? No, sorry, 6 for 11. Yeah, 6 for.
How did you do that? With the second derivative?
How do you
It's
do
just
it?
because CP is with respect to molar volume, so CP is the same thing.
Oh,
with respect to
true.
pressure.
Never mind.
I think. And this is easy to calculate because P is an explicit expression, so that's much easier to calculate. Typically, you would further rewrite this. And since I'll be doing that in the main course today, let's proceed to the main course. Clear on this?
Since we're going over that formula, can you show us how to do?
I don't have the time to do extra derivation, sorry.
No. I just
Come to me after if you have any question, but I can't do it. This is in a similar way we did this.
No, I just want to know if it's like a cubic function for V. How do you get the double derivative term? I know.
That's what I said. I'm going to do something similar to what you do with this, something like that in the main course. So please wait for the main course, which are starting right now. Okay? It's the last step of the main course. So hold your horses. I'll do it on the more important problem. And if we have expressions, I showed you last time, I have a volumetric equation of state. H and S, I can calculate immediately U, A, and G. So I have all 8 state bases. Okay? So, how does Unison, for example, evaluate H for the substance that we have? Other than having the reference state being the heat of reaction, the heat of formation. So, evaluating H of Tp from volumetric equation of state, which means function of, which is typically going to be P is a function of molar volume and temperature, and Cp star of T, the information we normally have available. So we'll follow a total of 5 steps. And I want to make sure that you understand every single step. The outcome, the final outcome, will be that for each equation of state, we'll be able to get a specific expression. For example, final result for Peng-Robinson using the equations I wrote on the board last time. Okay, we have that H minus what it would have as an ideal gas at a given temperature and pressure. So H at the given temperature and pressure equals H ideal gas at the given temperature and pressure. And the difference, as was correctly corrected by Jamie last time, is called the departure enthalpy. Turns out to be RT Z minus 1 as the compressive factor plus temperature, the derivative of that A that we have with respect to temperature minus that A over 2 square root of 2 of B times ln of compressibility factor plus 1 plus, careful here, this is a Z. My Z sometimes look like 2's, or my 2's look like a Z, so careful, that's a 2. Times B over Z minus 1 plus square root of 2B. And that's equation 6 for 29. So for any cubic equation, a cubic equation of state, we can at the end get an expression like that, which immediately calculates. Yes, Josh?
Is it possible in your Z's if you put like a line through the middle?
They're all Z's except for those two others.
Okay.
What about the denominator?
Huh?
The denominator.
Oh yeah, that's also this. Sorry, you're right.
Both of those are 2's, right?
Yes.
Okay.
Yes, yes. Sorry. All right, let's move on. So, our starting step is defining a path between temperature and pressure condition 1 and temperature and pressure condition 2. Let's take in the temperature pressure space any 2 points so I'll write pressure on the y-axis, temperature on the x-axis, and let's say I'm going to be calculating the change in enthalpy between state 1 and state 2. Important principle of thermodynamics. You can choose any path you want between 2 states. The change in state variable is path independent. So, I will follow a path that will change the temperature at pressure 0. So the path I will follow is starting from state 1, which means what? This is T1, this is P1, this is T2, this is P2. Okay? I'll follow the path shown with the red line. This way keeps temperature constant while I change from pressure P1 to pressure 0. Then at pressure 0, I will increase the temperature from T1 to T2. And then at temperature T2, I will increase the pressure to P2. So that's the path I will follow. Notice that the change of temperature happens at pressure equals 0, ideal gas conditions. Why we're doing that? Because I know completely Cp star of T. At that path, this part here, Cp is Cp star. Is that clear? Okay. We will start from the equation previously developed, that dH equals Cp dt plus molar V minus T partial V with respect to T at constant pressure dP, which is equation 6222. Okay? So I'm going to work with H at condition 2 minus H at condition 1. And that's going to be H molar at T2, P2, that's the H at condition 2, minus H molar at T1, P1. The total change in H from 2 to 1 can be rewritten as the change from here to here, plus the change from here to here, plus the change from here to here. So I can rewrite that as H at T2, P2, minus H at T2, comma 0. Plus, so that's the first path. That's the first section, or the last section, or whatever you want to call it. Plus H at T2, comma 0, minus H at T1, comma 0. So that's this one. Plus H at T1, comma 0, minus H at T1, comma 0. How do I get the difference in H? By integrating the H. In this path, temperature is constant. So for this path, since temperature is constant, I will have that dH is equal, the bracket, you allow me not to rewrite it, dP. In this path, pressure is constant. Pressure is 0 and constant. Yeah.
On the last bracket, would it be T1 P1 minus T1 comma
Did I mess up?
0? I'm asking you, I'm not sure.
No, because you're starting from T1, 0.
Yeah. No, this is the end point. Well, you have to follow the arrow.
Okay.
So the end point is T1, comma 0. The beginning point is T1, P1.
Okay, but on the first one, the end point was.
T2, P2.
Okay.
This is the path. Follow the arrow.
Okay, I see it now, sorry.
Yeah, no, good question. Anybody else? Okay, let's continue. In this path, pressure is constant. So that means in this path here, in the middle section, dH is Cp dt, and as a matter of fact, we know that Cp is Cp star, so that's going to be equal Cp star of T dt. And in this path, we go back to constant temperature, so it's going to be dH equals bracket dP. So that means that H, oh sorry, forgot. Better? Remind me if I forget it. H at T2, P2 minus H at T1, P1 equals. So, the integral here of the bracket, so that's going to be an integral from this point, which is T2, comma 0, to T2, comma P2 of the bracket dP plus Cp star plus integral here t1, 0, t2, 0 of Cp star of t dt. And here we have plus integral. I'm starting at 1 and ending at 0. So t1, 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 0 of the bracket dp. If anybody has a question, please ask. Ricardo, how are we doing? I can okay? David? All right. You should know that you can flip an integral by changing the sign. Integral a, b, anything is minus integral dA of the same. So I'm going to flip this to make it integral t1, 0 to t1, p1. So that means that this guy can be rewritten as minus integral t1, t1, 0, t1, p1 bracket dp. Okay. Okay. Now the next point is going to be a delicate point. That's a very important point to understand. I'm going to rewrite the middle term, which is really at pressure 0. But here, the whole thing is at pressure 0. I'm going to rewrite that result as a difference T2P2 minus T1P1. I will put a pressure dependence. So that's an interesting key point to understand. Integral of Cp of T1, 0, T2, 0 of Cp star of T dt. Okay. This is what? This is the difference. This is ideal gas pressure. This could be the difference, and for ideal gas, dH, ideal gas is what? Yeah, let me write it. dH, ideal gas, is Cp star dt. Ideal gas has no pressure dependence. With me? So this is really H, ideal gas, at T2, 0 minus H, ideal gas, at T1, pressure C. But H ideal gas doesn't depend on pressure. So I can rewrite that as H ideal gas at T2 minus H ideal gas at T1. And now here is where I'm throwing a little bit of curveball. It doesn't depend on pressure, right? So whatever pressure I put there doesn't change. That quantity I can write as equals H ideal gas at T2, P2. It's still correct. Vary any P2, it's still the same thing, right? Minus H ideal gas at T1, P1. Same thing. Seems weird, but you'll understand why shortly. And when we do the entropy next, it won't be so simple, as we will see. It will be a little bit more involved when we do it. But do you understand that that integral can be rewritten, even though why I'm doing it that way, my dear listener right now, can be rewritten as H ideal gas at T2P2 minus H ideal gas at T1P1. Because ideal gas is independent of pressure, I can do that.